Welcome to Breadboarding. Here's where we left version 1 of the Breadboard PC back in January. And since then, I've done a small series on programmable logic devices, which seems to have gone down well. And what I've been working on during this time is looking at rebuilding the Breadboard PC and trying to tidy it up a little. Now, the Breadboard PC was growing organically as I understood how the original IBM PC was built. And we managed to finish off getting it running Microsoft Windows 3.0. You'll see over here I've got a modern SATA hard disk connected to a SATA to IDE converter, and we've also got a 1.44 megabyte floppy disk, and we've also got down here a CGA compatible video controller, and in the early stages of the project I also built a monochrome display adapter one, which was a sort of stepping point to CGA one. So this is the Breadboarding Labs Breadboard PC 8088 version 2, and this is the introduction video number 1. So the Breadboarding Labs channel I started around August 2022 with the Nanocomp 6809 project. And what I was setting out to do is to build reliable digital electronics projects using good quality breadboards. I tend to use the busboard prototype systems, ones which I buy from Mouser. And the Breadboard PC version 1 project ran from December 2022 to January 2025. I think covered about 65 videos in total. And one of the key things about this project is I was learning how the original PC was put together and built. And hopefully this project can be a little bit quicker because I've already got a completed design to work from. So the IBM PC was released in October 1981. It used the Intel 8088 version of the 8086 processor. This was the same to program but had an 8-bit external data bus rather than the 16-bit data bus for the 8086. This meant that it was a bit easier and cheaper to build computers using it. There are a number of 8086, 8088 breadboard projects out there, and I did find after the previous series one PC-compatible 8088 breadboard project, although the VGA card for this only did text, it wasn't capable of doing graphics, so wouldn't have been able to run early versions of Windows. So I include the links to these two YouTube channels for those projects, if you want to just catch up. Most of the BB8088 is in fact the advent of code 2020. Most of the videos relate to that rather than actually building the PC. This was the original IBM PC prototype, and this used a wire wrap board. So this is the top side of the board, and you can see a lot of the decoupling capacitors wired between the power pins there. But on the reverse side, then you can see that it really was quite complicated. So in fact, I don't think the version 1 of the Breadboard PC, the wiring there was considerably more straightforward than the original PC wire wrap version. Now there'll be a link to the project completion video 65 at the top of the screen here and in the description below. So if you want to go through the detail of what I covered here, then you can look at that video there. But I'll just summarise the key things here. So the version 1, when it was completed, we managed to get MS-DOS 330 working, Windows 1, Windows 2 and Windows 3 working, although this with the CGA video card, then this was only able to do black and white video in Windows. We used the XI8088 BIOS by Sergei Kislev, and this was really easy to get to grips with and to configure it for the Breadboard PC purposes. In addition to the monochrome display adapter that I showed in the overview, we also created a CGA video controller, and this was 100% PC register compatible. The only bits that was different really is the frequencies that this ran at were to drive external VGA monitors, since CGA compatible monitors are a bit more difficult to come by and difficult to capture video from. It also supported the 40-column mode and also the graphics modes. This is the high-res graphics mode, which was also used for the Windows versions as well. Now, a lot of people who've tried to reproduce some of Ben Eater's Breadboard CPU project have run into power problems, and I have done some videos in this in the tips videos in the past. So I use a bench power supply. Now mine has been set at a maximum of 5 amps for this project, and I have cranked up the voltage to about 5.4 volts. You can see here I've got a good power distribution block here, and there are wires coming from here to the specific breadboards around the PC. And you can see I've also got these joiners for where the breadboards are joining at different angles. And around the place, I've got small digital voltmeters. So generally, as long as the voltage will be 4.5 volts or higher, then you shouldn't run into any problems. You can see here it was running with about 4.1 amps, and it would spike at about 4.7, 4.8 amps at power on as the hard disk spun up and if the floppy disk was being accessed. One of the commenters in the middle of the series recommended me to replace some of these DuPont cable single pin shells here with these multi-way shells. So this is an 8-way shell. And this actually was a great tip because plugging in a 8-way bus connection like this is a lot more reliable than doing it individually. I may have actually gone overboard on these DuPont cables, as I'll discuss in a few slides. So the original Nanocomp 6809 project included a ROM-based monitor, which I reverse engineered and decompiled into 6809 source code. I also, during the previous project, converted this into 8086 assembly, and this was quite useful in that it allowed me to get a basic debugging environment up and running before the video controller was running and before I was able to get the floppy disks and hard disk controllers working. And the monitor had some basic commands: inspect memory, execute, save to serial port, load to serial port, and inspecting registers and various other things. One of the other things that the original PC didn't include a power on self-test port. However, the XI8088 design did include a post port, and this was actually quite useful in that when adding it to a logic analyzer, then you would actually get these power on self-test codes as the system came up. And if you cross-referenced it to the list that was included in the BIOS, then you'd be able to tell at what stage the BIOS had actually got to if it actually came across a problem. You can see 0x30, for example, would indicate that it's starting to test the RAM, for example, if it was to halt at that point in time. So there were some improvements identified in that completion video as well. So probably the biggest issue is DMA. Now, DMA is direct memory access, and it's dedicated hardware for transferring data between memory and peripherals, normally floppy disk controllers and sometimes hard disk drives. Now, the original PC included the Intel 8237 DMA controller, and this is actually still included in 486s up to the modern day computers emulated in the chipset. So you'll find that the modern computers can still emulate this particular DMA controller. Now, as a book I referenced in the earlier videos where it did a comparison of how many clock cycles were needed to transfer data per byte, and I think using the processor used 39 clock cycles, DMA used 10 clock cycles. So DMA in the very early stages was about 4 times faster than using the processor. However, by the time we got to 10 MHz 286s, then that was 5 times faster than the original 4.77 MHz PC. So in actual fact, DMA was then slower than using programmed I/O, where the CPU is actually doing the data transfer. Now, there were 2 low-end PCs, the PC Junior and a Tandy 1000 didn't use DMA, and the Wikipedia article does say about the PC Junior, the BIOS routines for handling floppy access were different and more complex than those on the PC. We'll come back to that in a minute. But I had a lot of trouble trying to get the DMA working with the floppy disk controller. So the default PC BIOS floppy disk routines rely on DMA for transferring data to and from the floppy disk drive. I could get IBM PC DOS 2.1 to boot because it was quite small, about 44K, but I couldn't get later versions of DOS to boot, and I'm assuming that it's because they required more data from the disk. And at the time, when it got to later on in these files, the DMA controllers were getting confused and reading the data in the wrong order for some reason. So I replaced the DMA with programmed I/O, so using the CPU to poll the floppy disk controller. Now, the only problem I ran into is the PC Junior only had to deal with a 360K floppy disk drive, so that has a data rate of 250 kilobits per second. Now, the 1.44 megabyte floppies have a data rate twice that speed, and that means there's half the time available for the CPU to process the data from the floppy disk. And in the end, what I ended up having to do is to overclock the 8088 slightly. So although the default PC was 14.3 megahertz, which was based more on the CGA NTSC color video output to US style TVs, I was able to overclock it from the 15 megahertz, sort of its maximum rated value, to 16 megahertz. And that gave us about 22 nanoseconds quicker time in polling the floppy disk controller, and that allowed us to use programmed I/O. So in fact, the changes necessary to the BIOS was only about 500 lines of code. So it took me about 3 days or so to get these changes working. So I really would have to disagree with the article on the PC Junior saying it was more complex. It probably would have been a lot easier for all concerned to actually use programmed I/O rather than DMA in the early PC designs. And in fact, during the video, I showed that the schematic where DMA specific logic is included, those crosses indicate where all or some of the functionality of these chips could actually be removed by removing DMA. So I'm not going to implement DMA in version 2. I'm going to be using programmed I/O, and that's going to reduce the chip count by probably some 5 to 7 chips. One of the other problems I had during the project is I hadn't put enough data bus buffers or any bus termination. And you'll see here I ended up piggybacking another buffer chip on top of the original bidirectional buffer. And you can see here that the output of the oscilloscope for the CPU and from the bus, that there was a bit more interference. And so I think I certainly need to include more bus buffering. And also the compact Despro 386 included quite a bit of pull-up resistors for bus termination. And you'll also see that the IBM PS2 Model 80 also had quite a number of pull-up resistors. Now, one of the things I used in the version 1 project, I used the breadboard power rails as sort of bus rails. And one of the problems is that the connectors would sometimes come loose. So you can see here there's these two-way DuPont cables I've got plugged in here, and that sometimes these would come loose. Now, the two-way ones were much better than the individual single ones, but they still sometimes came loose. And also, where I was using these DuPont cables with the 8-way shells, there are some times where I think it would have been better just to wire in the links like this, the hookup wire, rather than using DuPont cables for these sort of short hops. Certainly, it would be a lot easier to see what was going on the PC from above if I didn't have quite so many ribbon cables. It's still perfectly valid to use these DuPont cables for runs going across multiple chips and going across the boards, but not so much for these short distances. One of the other odd things I came across is the real-time clock using this Dallas Semiconductor DS12885, that when it was powered off, then it would keep timing quite nicely. And this is the oscilloscope output of the crystal oscillator when the power was off and it was running off the 3-volt battery. But when the power was on, you can see there's quite a lot of interference actually with the clock, and this caused the clock to run fast. Because the data bus lines were right next to the crystals here, then I think that was what the problem was. That's something we're going to need to try and address during the version 2 project. When I was installing later versions of Windows, I had some problems with Windows 3 in particular, where it would corrupt the hard disk during the installation. And when I then ran the disk test utility from the original XT IDE project, which was the design of the IDE controller that we used for this particular project, it actually indicated there were some problems where I've highlighted them here. So you can see that it was working a lot of the time, but then there are certain patterns and things here that it was actually coming up with errors. So there probably needs to be a bit more investigation. And I think the data bus buffering I was talking about earlier may have been involved in that. There was another issue ran into with the floppy disk controller. Now, I was using a 40-pin DIP chip that can plug into breadboards, and there's also a surface mount 44-pin chip as well. Now, what I didn't realise at the time is that there's 2 extra pins on the 44-pin for the disk change signal coming out the floppy disk drive and disk change enable. And I didn't realise at the time, but I had to modify the BIOS so it didn't take any notice of the disk change configuration. And so what we need to do is to modify the design to allow for reading the disk change status in the BIOS, so that the BIOS can read the disk change status by reading bit 7 of the floppy disk controller when using the LDCR line. So the changes for the breadboard PC, I'm going to try and simplify the PC design and layout. I'm going to be trying to use new components where possible. In the version 1, I was trying to use legacy 1980s parts where practical. There were some like dynamic RAM where it didn't make any sense to use it. However, in this one, I'm been trying to use modern parts that mainly I've acquired from Mouser. And if I just show you the parts that I've currently got and show you which ones are new and which ones have been acquired through eBay and Silicon Arc and sites like that dealing with second-hand chips. So probably the most important one on the right here, it's difficult to read the labels on some of these things. Some of them are quite clear here, but others are quite difficult to read. Over here we've got our 80C88 Intersil chip. So this is a modern chip, still being manufactured. I think they're about £40 at the moment. Then we've got two modern Intersil interrupt controllers. So this is the 8259. This is our real-time clock, the Dallas Semiconductor one. This is the 8284 Intersil timer chip, which is still being produced. Then we've got two 512K RAM chips, these are static RAM chips. So in the version 1, I only included 512K of RAM. In this version, what I'll do is I'll include at least 640K of RAM and will also allow upper memory areas to be used if there's areas of memory not used by video controllers, for example. Then we've got a 32K electronically erasable read-only memory, and I tend to mount these in a zero insertion force socket. It just means that when we're programming the BIOS and making changes, when you're taking it in and out all the time, you don't bend the pins. Now this is one that if you've seen any of the programmable logic design videos, then this is one where I've actually managed to use the ATF750C programmable logic device to replace both the Intel clock generator and bus controller chips, so the 8284 and the 8288. Now those two chips you can only buy second hand. I don't believe you can buy those new anymore. So to be able to replace both those chips with this single sort of £4 or £5 PLD is definitely worthwhile doing. I'll come to this one in a minute because I think this requires looking at things under a microscope. And over here, we've got the legacy chips I've had to acquire through eBay and through other sort of sites such as Silicon Arc. So this is the Western Digital floppy disk controller chip that I was using. This is the VIA PS2 keyboard and mouse controller. This one over here is the VGA compatible video digital analog converter. So this basically takes the digital inputs for the video signal and produces the voltages necessary to drive VGA monitors. And this one down here is the cathode ray tube controller chip. So this is the Motorola 6845 compatible Hitachi device. Now this one has a few extra features and is also able to work at faster frequencies that are compatible with VGA. Now I'll just come back to this one. Now up till now I've always been trying to use DIP dual inline package chips that are easy to plug into breadboards. But when it came to the serial controllers, I couldn't find any new serial port devices, and I thought it was probably a time to actually try these out. So this is a Texas Instruments 16C550 serial chip, and it's quite difficult to see here. It's so small, it's only about 7mm along each side here, but these are some Adafruit 48-pin adapters, so TQFP48. And in fact, if we switch this over to the digital microscope I've got, you'll be able to see in close-up what this has actually got. Just turn it around so the label is... So you'll see this is the Texas Instruments TA550DI, I think, is part of the label. I have got the packaging here, which the full name of it is a TL16C550DIPT. It took a little bit of research on how to solder these onto these sort of DIP adapters, and I perhaps might do a video on that later on in the series. There are plenty of videos out there on how to solder these types of chips onto these sort of DIP adapters, but this is a first for me, so we'll be covering that as we go through the series. And those DIP adapters, get them from Adafruit, or I think I got mine from Pi Hut over here in the UK. And these do both the QFN and the TQFP, and you provide your own pins and solder it. So they took probably about an hour or so to solder this. I also tested continuity against every pin to every pin on the surface mount chip just to make sure I'd made good connections, and that all worked quite well. So the other thing that I mentioned was using the breadboard power rails as buses was all very well, but there were problems in that you could only plug 2 wires at a time and they tended to come out. So what I've done is I've got a large bit of strip board, Vero board here. Just move the camera out a little to see a little bit better. So this is the widest Vero board, strip board you can get, so it's about 8 inches across. So I think there's 78 tracks. And what I have done is I have soldered in 9 rows of 0.1 inch connectors on there, and I have actually gone through and tested the continuity between each row and each pin and made sure there are no shorts. So that's what I'm going to be using for my bus connections, and what this will mean with the appropriate socket connectors to plug into the end here, then this should be more reliable and we shouldn't have as many problems with stray leads becoming disconnected. The other thing I've been looking at is the keypad that I used. In the early ones I had actually built on Vero board similarly, but this Adafruit NeoKey part is quite a nice thing. It actually comes with the board already made. It can be broken up and cut into smaller keypads, but I thought I needed a 5x5 keypad. I'm not using this row here because I might want to reuse the keypad for something else at some point in time. And you can see these are just standard cherry key switches that just can be unplugged and pulled into this, and the little connectors at the back here provide the electrical continuity. I've had to solder in a number of 0.1 inch connectors on there to actually hook up the various leads. This can also actually do different color LEDs. You'll see here the little white bits here are red, green, blue color LEDs, but you need to hook this up to a microcontroller to be able to do that. But this should hopefully mean that the building the keypad and the 7-segment display should be much quicker and much faster using off-the-shelf components like this. And it just comes with standard key caps that we'll put in there. So that's something else that we've done recently. So showing you that we're looking at using these surface mount parts for the UART, for the serial controller. We'll be using the strip board for the headers for the bus connections, and that will also allow me to use the permanent connections for the data address control buses for the logic analyzers, make it a lot easier to put the logic analyzers on there. Got to also redesign the circuitry that access the keypad to use the NeoKey keypad. Originally, I used the same chips that the Nanocomp 6809 used, so the 6821 parallel port and the 6850 serial controller. So these are now going to need to be rewritten in the Nanocomp monitor to use the PC compatible UART, and I've also replaced this parallel port just with some 7.4LS logic chips and some PLDs. Don't really need to have a more complex chip like that. And of course we're going to also remove the DMA and use programmed I/O for the floppy disk drive. So to summarise the version 2 design, so the operating system, we're going to be using MS-DOS 3.3.0 and Windows 1, 2 and 3. We're going to go straight to the CGA graphics controller. They're not going to bother with the monochrome display adapter, although this will not be timing compatible with the original CGA controller, so it won't run some of the 8088 MPH type demos, but it will produce VGA compatible video output that will be able to go into modern monitors and video capture cards. From the original 81 PC and PCXT, we've got clock, CPU, bus control, and the timer and parallel port B and speaker. We've removed the DMA over version 1, so that's taken probably 7 or 8 chips out of the design. From the PCAT era, we've got the real-time clock and the 16450 compatible serial port, although we're using the slightly more advanced 550 version. Then we've got the dual interrupt controllers, which allow us to include the mouse and the real-time clock. And then the IBM PS2 introduced the PS2 keyboard and mouse and the keyboard and mouse controller. and also the 3.5-inch 1.44 megabyte floppy disk drive and controller. Just a small point is, strictly speaking, this is a 1440 kilobyte floppy disk, which is slightly different from 1.44 megabytes, but most people know it as 1.44 meg floppy. And finally, the Compact Desk Pro 386 introduced IDE disks, and so the IDE disk controller, and we'll be using a modern SATA disk with a SATA to IDE converter on it. Now, one of the reasons why it's taken me a little while from the end of the previous series to producing this video is what I've been doing is working on the schematic diagram. So this is KiCad, and what you'll see here is we've got the whole design from day one, really. In the previous series, I was building out the processor and the clock and the reset logic, and then I'd add extra bits and it would grow quite organically. Whereas what I've been able to do here is design it all from day one. And the layout's been optimized, I hope, to make things a bit simpler to hook up. You'll notice that in the middle here, this is where our bus is going to go. So where our 78 lane bus is going. And what we've got is the 7-bit data bus, although there's enough spare lines to be able to bump that up to 16 if we want to upgrade the processor at some point in time. We've got the 20-bit, the address bus. Control bus includes things like IO read, IO write, memory read, memory write, and the reset signals, amongst other things. Then I've got a bus for the chip enables, so that the address decoder here provides a number of chip enable lines here. And the advantage of that is it means you don't have to keep on including all the higher address lines being decoded all over the place. And then finally, all of the interrupts, and then all the interrupts that are needing to be accessed across the board are then actually in the top area of the board there. And this now includes the programmable logic device that we've got to replace the 8284 clock generator and the 8288 bus controller. So this chip is able to do the job of both of those. And those two chips you don't really have to buy second-hand on eBay or through other sources. You can't get them new these days. We've got all the similar data bus buffering, but also buffering the control bus signals, address decoder. Then we've got the power and self-test port, real-time clock, and the port B read and write stuff. Got the chip here that does the speaker timer and also some of the wait states. And then we've got a much simplified area over here. So we've taken all the DMA out. So we've just got two interrupt controllers and the data bus buffer for these controllers and all the other chips over on the side here. Down the bottom here, we've now got 1 megabyte of RAM. So the higher RAM will fit around the video card, so we can actually use some of the upper memory area for later versions of DOS. Still got the same EPROM for the BIOS. And then this is the redesigned keypad and 7-segment display. So very similar design, but this now, rather than using a parallel port chip, just has the 74LS646 latched buffer and a couple of PLDs and a couple of other logic chips. So that should be simpler to program. Then we've got the CGA video controller here. This is very similar to the one that was developed in the previous series. There will be a few minor changes to this, but fundamentally this will be remaining the same. Now this section now consolidated a lot of the external I/O type functions. So we've got our new serial port using that surface mount chip with a USB to PC serial converter there. Then we've got the PS2 keyboard and mouse controller with the PS2 ports there. Floppy disk controller with the floppy disk connector there. And we've also now implemented the disk change logic that we need. So now the logic here will actually handle reading the disk change status from the BIOS. And then finally the IDE hard disk controller. So the IDE port here will be plugged into our IDE to SATA converter, and then the logic around here supports that. This is the I/O port decoding for a lot of the external logic chips here. So it's effectively like an old-fashioned multifunction card, which has the disk controller, floppy disk controller, serial port, and it also has the keyboard controller on it as well. So I've got a high-level plan, very much similar to what we did previously. So a basic Nanocomp 8088, that has the LED display keypad and the monitor, and with the new serial port that allows us to upload and download data across the serial port. Then we'll build it out into the basic floppy disk PC with the host port, keyboard, interrupts, real-time clock, floppy disk controller, and we should then be able to boot up MS-DOS from floppy disk. And then the final stage will be to add the IDE disk, booting from hard disk with MS-DOS, building the CGA video controller, setting up the mouse, and then running Windows. So if you don't want to miss out on the series, then please hit subscribe. And if you have a look at the playlist for this, then you'll be able to look at the playlist to go through all the videos sequentially. So thanks for watching, and if you can hit like as well, it just helps to make the videos available to more people.